Today I'm going to be talking about atomic layer etching, abbreviated ALE. It's been in development in lab scale research for a decade or two, but is now just finally starting to see a turning point in needs for industrial use. So we might see this now starting to appear in current and future process development. ALE is the etch analog of the more commonly known ALD, which of course stands for atomic layer deposition, where alternating precursors are used to form individual monolayers that react on the surface to deposit a film, one atomic layer at a time. ALE is going to do the same thing, only subtractively, and remove one atomic layer at a time. This type of processing provides a valuable option in the process developer's toolkit for transferring critical dimensions to the substrate, and also for providing better etch stop control. So we'll start with talking about some of the reasons why we would want to do ALE, and then go into a little bit more about how it's done and some of the challenges. So in a self-aligned double patterning FinFET flow, we are going through several different etch steps in sequence in order to create our final dimensioned fin. And we start with the litho patterning, which of course needs to create a nice pattern for transfer to etch. But one thing that's interesting about this flow now, as we go and perform double and even going forward we may see quadruple patterning, is with each subsequent etch transfer to a new hard mask layer, we can introduce errors in the line that get propagated and made worse in subsequent etch steps. And so this shows up as line width roughness. We often talk about the idealized case of what a fin should look like, but when we start to do the measurements on the actual devices that are produced, we see that there is variation within them. And so what was intended to be a straight line might not come out perfectly straight. And we see here's a top-down image of a line and a tilt-sem 3D view that shows some of this roughness characteristic. And so these types of imperfections can show up, as I mentioned, in the litho patterning, the initial litho patterning itself, but also in any of the subsequent transfers through etching. Also of note, as Moore's law progresses, line edge roughness or line width roughness become a more significant portion of the CD budget. So back when we had 1 nanometer of line edge roughness on perhaps a 45 nanometer or larger transistor, this wasn't significant. But as we move towards 10 nanometer transistors and smaller, obviously the same amount of roughness becomes a growing percentage of the width, and it becomes more critical. It has more impact on the transistor's function. So just a note on what these values mean and how we measure them. When we're looking at a line on a SEM, the SEM tool can create different measurements at different points. In previous technologies, we might have only looked at the mean of those measurements, but now with the criticality of this roughness, we can also look at the sigma of these individual measurements, and that is what the line width roughness actually is. In order for this line width roughness to be minimized, we need to start with a good litho mask. But the etch process can also negatively impact this line width roughness parameter. And it can do that through UV exposure from the plasma, ion bombardment that shaves off the edges, and also from heat damage. Resist typically deforms above 130 or 140 Celsius, and so if the temperature is not regulated during the etch process, that can deform the mask. And once we end up with a transferred pattern that's not straight, and we have this line roughness, we could have a situation like this where each transistor actually has a different gate length, and the leakage current is known to increase exponentially with increased roughness. So we want to try to minimize this roughness parameter. And using ALE is one method that we can look to do this. And I like to think of it as, rather than going in with a chisel, we're going in with a scalpel. We're going to try to remove just a single atomic layer at a time, and that will do a better job of guaranteeing the transfer of the pattern that was delivered from the lithography starting point. Here we have a TEM cross-section of a TSMC 28 nanometer process that is done with a gate last process flow, where this hafnium oxide layer is deposited before the polygate is hollowed out and it's placed by these tantalum and other subsequent metal layers. So if we wanted to go and hollow that out without damaging the very thin layers below, which are approaching single-digit numbers of atoms at those layers, using ALE might be a good choice here for allowing that controlled etch. Also, for a contact type process, touching down to our sources and drains, is typically an oxide etch that has a nitride etch stop where it meets the source and drain. This might be another good application for ALE, where we're trying to clear the nitride in a very controlled, gentle manner without damaging the source and drain substrate below, which will help improve the contact resistance. So let's take now a look at the process overview of how we would create an ALE etch. But first, I'll compare it and contrast it to a standard etch process. So this is just a quick look at a CCP, or capacitively coupled plasma etch chamber, where we have feed gases coming into a shower plate. There's RF being delivered to a lower electrode where the wafer sits, which would be on this typically an electrostatic chuck that holds the wafer down, also provides some cooling to the wafer. And we have a plasma that gets generated within the space between the electrodes. So this RF will power this electrode, the upper and walls will be the grounded electrode, and plasma is generated between them. When we have a plasma generated in the chamber, we have the highly mobile electrons will end up moving quickly to the walls and charging it negative. The wafer will develop a negative bias, and there will be a plasma sheath that is formed surrounding the plasma between the electrodes and the plasma. And in that sheath, it's a dark space with a lack of electrons. Positive ions from the plasma are going to be accelerated across that sheath with high kinetic energy and bombard the wafer in an anisotropic manner to give a directional etch. So the directionality and the profile control tends to come from the ion bombardment in that vertical manner across the sheath, and that's shown in this red line here. But there's also a chemical component of plasma etch. Within the plasma, we're also generating radicals. Those radicals are going to diffuse isotropically to the surface, where they're going to adsorb and react with that surface and cause chemical etching reactions to occur. This is an old experiment from Coburn and Winters from 1979 that demonstrates a little bit of the difference between the sputter and the chemical etching portions of the etch process. This is actually done using xenon difluoride, a peculiar gas. It violates the standard rules that noble gases don't form molecules, but this xenon difluoride gas actually can react without a plasma with silicon, and it will dissociate, free the xenon. Fluorine will attack the silicon surface, and SiF4 will evolve as a volatile byproduct. So with subjecting a silicon substrate to the xenon difluoride gas, we get a chemical etch in this portion. In this experiment, they turned on an argon ion beam, which introduced ion bombardment combined with the xenon difluoride gas. So they keep the xenon difluoride on until this point, but in this middle portion, they're performing both ion bombardment and chemical etching. And you see that there's a dramatic increase in etch rate, and when they turn off the xenon difluoride gas, it drops right back down again. So here's your etch rate from just the sputter. It's actually a little bit lower than the chemical etch rate, but it's really the combined effect where you get the high etch rate. That the synergistic effect, sometimes called the RIE effect. This is what has given plasma etch the benefit of processing for the last several decades. But this is what we want to reel in. We need to control this. This type of high etch rate can over-etch these fine structures with single layer precision that we're trying to perform here with ALE. So in order to do that, we need to avoid or minimize the degree that we have the combined ion bombardment and chemical etching. And so the way ALE does this is that it uses different stages. So we'll initially introduce reactive radicals that will absorb to the surface and attack the substrate, but it needs to be a self-limiting reaction. So this can't be a chemical reaction that's going to continue to spontaneously etch and keep etching on its own. Ideally, it's a reaction that forms a passivating monolayer on the surface, but that needs that ion bombardment to help desorb the molecules and the volatile byproducts. And so this reaction is like that, where by then having a purge step where the chlorine is removed from the system and introducing a desorption step with ion bombardment, argon ion bombardment, that'll desorb the silicon chloride from the surface and we can then have a purge step to ensure that desorption occurs, and we're left with a nice surface that has been modestly etched. So it can be a single, if you have an atomically smooth substrate to begin with, you can remove single atomic layers through this type of process. If there's some roughness to the surface, you may remove more than one layer in one pass. But it's a nice and controlled etch rate. So the criteria for performing this are that we need to have no secondary unintended reactions, such as UV exposure or damage from the plasma. And we need to have discrete unit steps, and the unit steps must be self-limiting. And these are criteria listed out by Thorsten Will, VP from Lam Research. Lam is one of the OEMs that makes etch tools. In these next couple slides, I'm going to show some of the results of this type of processing. On the top here, we see a continuous etch with chlorine and argon bombardment on a silicon blanket wafer, and you can see that there is some roughness to the surface. The atomic layer etch produces a much smoother surface. So AFM data confirms what we saw in that last TEM image. Before the etch and after the ALE, we see similar surface roughnesses, whereas the continuous plasma etch has a much rougher surface. We also see excellent cross-wafer uniformity is possible due to the self-limiting reaction. So normally within a plasma chamber, due to its radial design, sometimes the radical density and ion density will be different from center to edge. There can also just be different flow characteristics depending on the symmetry of the chamber, location of the turbopump. But here, due to the self-limiting nature of allowing enough time for the precursors to absorb to the surface, purging those out, then allowing time for the etched products to desorb, and doing it sequentially, we get across the wafer a very good uniformity. And also that by allowing that time for desorption and desorption, we overcome aspect ratio dependence issues such as RAE lag as shown in this image. Normally, a small feature may etch more slowly due to the difficulty of the etch reactant to get diffused into the finer feature and for the etched products to diffuse out. Using the cyclical process, though, we are allowing that time, and so this type of dependency goes away. And we also see problems such as microtrenching minimized, and we have a much more uniform etch front that propagates. So some of the challenges with ALE, let's go back to our list that was presented by Thorsten Will of Lam. The first one was no secondary unintended reactions. So the question will be, are new tools required, or can this be done with existing hardware? So some of the ways that we may look to do the cycling, it would be to introduce, rather than receiving the radicals and the ions from the same plasma source, we may choose to use a downstream plasma to generate the radicals and have them enter the chamber separately. Or also, we may see the use of neutral beam etching coming into play. Neutral beam etching introduces a high aspect ratio grid that neutralizes electrically the ions as they pass through by having specular collisions with the charged grid walls that neutralize their charge, but they still have they maintain their vertical orientated kinetic energy heading and still strike the wafer. So this can provide a more controlled physical desorption step. And it also separates the UV exposure from the wafer by introducing this grid array, or by using a downstream plasma for the radical generation. Discrete unit steps are required. So the addition of purge times here is actually the biggest impact and disadvantage to this process because it introduces large run rate impacts. The purge steps after the radical introduction and after during the desorption stage can range from 30 seconds to 2 minutes, and depending on how many cycles are required, that can create some pretty long etch times. So this may also drive further hardware improvements, such as the need for fast gas flow switching and high pump speed on the equipment to minimize those purge steps. And finally, we require the unit steps to be self-limiting, so new precursor chemistries may be needed, and new precursors may be needed for selective etching of new exotic materials, such as 3,5 fin materials, or we may see this type of etching be useful for use in graphene or carbon nanotube devices. And so it still remains to be seen if ALE will prove to be necessary and when. The original equipment manufacturers of the etch equipment expect that it'll be necessary at 10 nanometer node and beyond, and so they've begun to introduce hardware to enable this type of technology. And in order to use this, we'll need to have high selective etch chemistries matched to the types of films that are interested in being etched. However, those etch chemistries may still be able to be used with existing hardware without the need to add the pump per drum rate impacts of ALE. And other competing gentle etch processes like radial line slot antenna plasmas may prove sufficient to delay ALE implementation. Here are some references that I used in putting this presentation together. Thank you for your attention, and hopefully now you know a bit more about ALE.